Okay, I've written some general guidelines that are sufficient for graphing rational functions. And I kind of remember that glare or something makes it hard to read red when it's written up here. I just chose a part of the board that was blank enough that I could get all this stuff in. And I wanted to write it in the context of what we've done with these two examples. But you might have trouble seeing this. So I'm going to pull the board over. Now ignore what's behind it. That's multivariable calculus with high relevance to physics. Well, something's not very even here. It's okay, it won't hurt. Okay, so you can ignore this stuff. Very interesting, but it's way down the road from this course. Okay, so here it is. What do we do when we see a rational function? We find the zeros of the numerator and mark as the zeros of our r of x function. We've done that here. There are the two zeros of this function. And I did it over here. Here's the 1, 0 of the function that we have over here. That's just on a preceding video. Okay? And I know that sometimes a rational function with a simple linear numerator and a quadratic denominator has a denominator that factors, which gives you this kind of graph, or has a denominator that doesn't factor, which would give you this kind of graph. Okay, well anyhow, so we find the zeros of the numerator and mark as zeros of r of x. So that's marked here and here. And on this graph, marked here. Find zeros of the denominator and mark as vertical asymptotes. And that's like with a dotted vertical line, not a very straight line. I've done that here. So those zeros of the denominator give us the asymptotes. And you see how they're going to work out. Okay? Partition the x-axis with zeros of the numerator and denominator. So the x-axis partitions to the left of -9. There are no zeros or asymptotes, so the interval from -infinity all the way up to -9 is an interval where the sign of the thing doesn't change. Okay, because the sign of a numerator or denominator can only change by passing through 0. So don't have any zeros of the numerator or denominator to the left of -9. We don't have any places where the signs can change. And since the sign is negative just to the left of -9, it's negative forever as we go across here. Okay? Between -9 and -6, there are no zeros of numerator or denominator, so neither numerator or denominator can change sign so that the function can't change sign. The function is positive. You pick any number between -9 and -6 and verify that. You can be a little more sophisticated about it, but that's fine. I've shown both. Okay? And then same between -6 and 2. Okay? No zeros of the numerator, denominator, so no sign changes. And we find that the sign is always negative. Now, I listed find the y-intercept down here because I was thinking about other things first. Generally, you find that pretty quickly. So if you've already got the y-intercept, you don't have to do any more. You already know that in the interval that contains the y-intercept, the function's going to have the same sign it does at the y-intercept. And then to the right of x equals 2, again, no sign changes. And we easily find that everything is positive. All three factors here would be positive. Okay? And we could have done the same with the function I have over here. I've got the function off the board, so we're not going to look at it. But we did determine the signs are positive from here to here, negative from here to here. There are only two intervals for this function because the only zero of numerator denominator was -9. Okay. So we find the sign on each interval of partition, find the y-intercept if we haven't already, and it had better agree with the sign, if you do it later, better agree with the sign you found for the interval of the partition. That includes the y-axis. Okay. Okay. Then determine the end behavior, which is solely determined for most functions just by leading coefficients. In this case, x over x squared. The one common exception is when you have a quadratic divided by a linear, you can do the long division, or when the degree of the numerator is 1 greater than the degree of the denominator, your long division is going to give you a linear function plus some remainder, and you graph that accordingly. Okay, well, there we have it. Determine the end behavior. In the case of both of these functions, the function has to approach 0 as x approaches positive infinity or negative infinity. So we get either this behavior here with an asymptote here, or this kind of behavior. So there we have it. That's all you got to do to graph a rational function, come up with a decent graph of a rational function. Now you're also going to see some examples. One example, a mixing problem. It's not difficult to understand, but a rational function emerges out of that problem. Rational functions emerge out of many actual real-life situations, so it's important to understand them. It's also important to understand graphs well enough that you can reason through this sort of a process. It just gives you a broader perspective on graphs, and that's important. You don't understand graphs well. If you don't understand graphs well, you're not going to be able to take the information the graph gives you and use it. And graphs are, I won't say everywhere, but they're common in most fields. Okay? And they're important for everyday life. Okay, so there we have it. That's kind of a synopsis. Now I'm probably going to wipe out some of this stuff and do a couple more quick examples, sort of a review, and then a little bit about where we can go with this later.